All right, today we're going to talk about what happens when you take capacitors and put them together. And for the purposes of this, we're going to assume everything's a parallel plate capacitor, which just makes everything way easier. All right, so you should be familiar with the idea of series and parallel from last year. All right, which of these? The one on the left, is that parallel or series?
Parallel.
Right. Why?
Because it's parallel to each other.
Because it says parallel right above it. Exactly. No, because they're parallel to each other.
They're getting separate voltages.
Whoa. Wait, hold on.
Same voltage.
Yeah, here's the honest to goodness for real definition of what it means to be in parallel is this. They share the same potential on the left side, and they share the same potential on the right side. Why is the left side all at the same potential? Why is it all at the same voltage?
Straight connected to the back.
It's connected to the same piece of metal. Can you see that? This is all just a wire here, so all the voltage along here, everywhere along this wire is all the same. And then same thing with the right side. That's what it means to be in parallel. So if you had three in parallel, there would just be another wire down here connected to a capacitor and another wire down here connected to the other side of the capacitor. Does that make sense?
Yeah, the current just increases.
All right. So, I'm not going to talk about current yet. Parallel is all about the voltage being the same. All right. Now, if the voltage difference across the capacitor is the same, that means the voltage difference across this capacitor is the same as the voltage difference across that capacitor, right?
Yes.
Okay, fine. So that's easy. Current. Somebody mentioned current a second ago. Let's not talk about current, because current with capacitors is difficult. Instead of talking about current, let's talk about charge on the capacitor. Wouldn't you agree, if you look at these things, that the total charge between both of these plates would be the charge of this one plus the charge of that one? Doesn't that kind of make sense looking at it?
Yeah.
So if you wanted to make one big capacitor that could store the same amount of charge, what would you do to these?
You just add them together. And then
You just connect this line right here so these capacitors are connected. That's all you'd have to do. And you'd have one big capacitor with the same capacitance as the two smaller ones. Agree? So if you wanted to store charge, the total charge you could store would be just the sum of the two original capacitors stuck together side by side. All right? So that's pretty cool. Capacitors in parallel are actually really easy to think about because of that. All right? In parallel, you just meld the two pieces of metal together, and you've got a big capacitor that stores the same amount of charge as the two original pieces. Srini, you got this? Yes. All right. So the total charge stored by the two in parallel is equal to the charge stored by this one plus the charge stored by this one. Now, here's a question that I'm sure you didn't really think about last year, but I want you to think about now. It's kind of a basic question. Jack, you ready? If I told you that this side had positive charges on it and this side had negative charges on it, what's the total charge? So say this side had plus Q and this side had minus Q. What's the total charge on the capacitor?
is it plus Q?
Negative. It's 2Q.
Ah! What is it?
It's 1 billion.
2Q.
Is it 0? It's because plus Q plus minus Q makes 0?
But then you can do QT equals Q1 plus Q2.
You see the problem? Okay, it comes with the definition of what we actually mean when we say Q. The charge stored on the capacitor, if this side has plus Q and this side has minus Q, guess what the charge stored on the capacitor is?
Q.
Q.
Sweet.
That's what it actually means. Okay, want me to draw it?
Is it just a definition?
It's just because it's separated.
It's the definition of what it means. If you got charge stored on a capacitor, this side has plus Q, the other side has minus Q. The charge stored on that capacitor is Q.
Is
So
Q
for
a
plus 4 on one side,
vector
plus 4 on the other side.
Is Q a vector or scalar? That's a good question. Anyone know the answer?
It's gonna be
Neither.
scalar.
It's a scalar.
Okay.
Doesn't have a direction. Or does it?
Come on!
Scalar.
It actually
Is it?
does kind of have a direction. Because,
Because it depends on what voltage is there.
yeah, the high side and the low side, if you swap them, that would be different, right? So it kind of does have a direction to it. You say the charge is Q, but then you have to be specific about which side is the high voltage side and which side is the low voltage side.
Wait, is it Q? Because always one side's going to be the exact opposite of the other.
Yes, that's the key.
So if you swap them, is it still Q?
It's still Q, but the voltage, the high voltage side is going to be on the other side.
So we'll pretend life makes sense for a moment. And
All right, does that make sense? So it's got a magnitude that's defined by the amount of charge that's on either plate, because the amount of charge is the same on either plate, and then you go based on the voltage, which side is the higher voltage side and which side is the lower voltage side, and that can flip. Good? All right, so that's what you mean when you say a capacitor is charged. Both of the plates actually have charges on them. But you just have to pay attention to which is the high side and which is the low side. All right, so moving on. Let's see. So let's move on to total capacitance. We know capacitance is, the total capacitance for this capacitor would be the total charge divided by the total by the difference in voltage across it, right?
yeah.
Well, the total charge is Q1 plus Q2, right?
Yeah.
And the difference in voltage across it is just delta V, which is the same for both. Which means the total capacitance would be Q1 over V1 plus Q2 over V2, right? Well, Q1 over V1 is C1, capacitance 1, and Q2 over V2 is C2. Right? So the total capacitance are C1 plus C2. You just add them up. Good? So capacitors in parallel are easy. It's like resistors in series. Got it? And this is the actual reason why. All right, now the hard one. Series capacitors.
Just like voltage in general, because I think the voltage is fairly easy.
Yeah, voltage is easy. It's easier to decorate a picture with voltage than it is to decorate a picture with current, I think. But we're going to talk about how to decorate a picture. If you were in my regular physics last year, you know what I'm talking about. So, yeah, decorating pictures is fun and easy.
That's the best part.
Yes. All right, so here we go. Series capacitors. Ooh, scary, right? There is some magic that happens with series capacitors. You ready? All right. Okay, here's the hard stuff. Let's say you have two capacitors in series. You have a little one and then you have a big one. Which one's going to store more charge?
Equal charge.
The big
No,
one,
it's not
The
equal
one
charge.
with the greater potential difference across it.
equals the area of
The one that has the
area
greater
of larger.
capacitance.
What?
Wait, what one's gonna store more charge?
Okay. Here we go. We're going to take a
No, they're
vote.
gonna have the
We're going to
same
take a
amount
vote.
of charge.
Okay, so
Can you rephrase the question?
we have a little capacitor and we have a big capacitor. Who says the little capacitor is going to store more charge on it? Raise your hand. Who says the big capacitor is going to store more charge on it?
It can store.
C is always
No,
the
it's
answer.
they're in series. So which is going to? Who says the answer is always C? None of the above. Right.
Okay, now you go.
Why?
Depends on the type.
Why?
Because
Yes.
all the charge that came from the first one has to go to the second. It's just
Yes.
like current.
Say that again.
It's just like current. Oh, all the charge from the first one has to go to the second one.
Bingo. Okay, imagine this. These were connected to a battery, right? Now, all the electrons from the battery get pushed, say all four electrons get pushed to this side. So we got 4 electrons on this side of the little capacitor. How many electrons is it going to push away from the right side of the capacitor? 4. Right? 4 electrons should repel 4 electrons. So where do those electrons go?
To the right.
Onto the big capacitor. So how many electrons go on the left side of the big capacitor?
4.
So how many electrons get pushed away from the right side of the big capacitor?
4.
4. So you end up with 4 negatives here, 4 positives here, 4 negatives here, and 4 positives here. Well, so what's true about the charge on this capacitor versus the charge on that capacitor? They look the same. And in fact, not only do they look the same, they are the same. So if you have 2 capacitors in series, that means the charge stored in each capacitor has to be the same. And it's a law of conservation of charge. Or in other words, if you push a certain amount away, that means this next capacitor is going to have exactly the same as what you had on your left side. Right? Good.
So
All
do engineers rather what have capacitors stored in parallel or
Depends on what
It
you're.
depends
Or
on
what, I think doing stuff in parallel is a lot easier than doing stuff in series.
Yeah, capacitors, from a network analysis point of view, capacitors in parallel is easy. Capacitors in series, that's where you have to do the 1 over thing.
I think it's
No, we're going to talk about that in just a second. Give me a moment. All right, so because any charge that accumulates on the right side of C1 had to come from the left side of C2, et cetera, et cetera, et cetera, that means Q1 equals Q2 equals the total Q, quote unquote, for this mess of capacitors. The charge for this whole, the effective charge stored. Wait, Shiv, if I say this, does it make sense to you? The effective charge stored by this mess of capacitors is Q, which is the same as the charge stored by this capacitor and the charge stored by that. Okay, does that make sense? So we can pretend like there's one big capacitor that stores a charge of Q. All right, fine. Now, voltage difference, that's actually easy to figure out. All you have to do is realize if the left side of the whole circuit's at 0 volts and the right side of the whole circuit's at 9 volts, and from here to here it's a 3 volt difference, how much is it from here to here? 6. Yeah, this voltage difference plus this voltage difference gives you the whole voltage difference. Does that make sense? All right, good. So you have to add up the voltages across the capacitors in order to get the total voltage across all the capacitors in series. Good? All right, we're going to put those 2 ideas together like we did before, and we get the total capacitance. We know that the total capacitance is the total charge divided by the total voltage. Yeah?
Is the voltage thing the same for those two? 'Cause you
No, these are very different. V1 is different than V2 because they're different sized capacitors.
oh, those are equal on that one, right?
Yeah, the voltages in the parallel would be
I
like, if
can't
it was like
see.
12 volts, it'd be 12 volts.
Oh yeah.
That's it.
I'm only looking down.
All right, so here we go. Total capacitance is therefore the total the total charge divided by the total voltage, right? Total charge is QT, or Q. Total voltage is V1 plus V2. Well, let's see. Oy, this is not fun. Let's invert the above. 1 over the total capacitance equals the total voltage divided, V1 over Q plus V2 over Q. Agree? Which means 1 over the total capacitance equals 1 over C1 plus 1 over C2. You guys remember this from last year?
I hated that.
Which means if you wanted to solve for, if you have 2 capacitors, the math works out to be, if you do the common denominator thing, the math works out to be C1 times C2 over C1 plus C2 if they're in series. Sound good?
If it was 3, wouldn't it be C1 times C2 times C3? It would be over C1 plus C2.
No, it doesn't actually work that way. It would be, if you had 3 in series, it would be C1, C2, C3 over C1, C2 plus C2, C3 plus C1, C3. That's if you had 3 in series. All right? And you again, it's a common denominator thing. You have to do all the algebra to figure that out, but that's what it works out to be. If you had 4 capacitors, it would be C1, C2, C3, C4, and then every possible combination of 3 capacitors that you could make on the bottom.
Wow, that would get really big really quick.
Yeah, it's a mess. Which is why it's better to just invert all the numbers in your calculator. Yeah, 1 over C1, 1 over C2 in your calculator. All right. Okay, let's continue. Now, examples. What if you had a compound capacitor network? You had a 1 microfarad, a 2 microfarad, and a 3 microfarad. What would you do? Which would you combine first? Combine the parallels. What do these become? Those become 5 microfarads. So they become that, right? Now what do?
I have to do the 1 over.
And combine the 1 and the 5 in series.
5 over 6.
So, and it comes out to be 5, 6. Does that make sense? All right, I'm going to stop talking now. You've got 10 minutes left. I want you to get started. I'm going to point out a couple problems in your packet that I want you to do before the bell rings because they get really, really crazy, interestingly hard. All right, you know what? In fact, we might not take the test on Monday. I'm going to take a look because some of these capacitor network problems get really tough. All right, so anyway, I will get back to you on that.